Everybody. For those of you who just joined, welcome to the afternoon session of the second day of the NASA Gregory G. Leptoukh Second Online Giovanni Workshop. This is your host, Jennifer Brennan. I've got just about 2 p.m. Eastern Standard Time, so I would like to go ahead and get started. It is my pleasure to introduce our first speaker for today's afternoon session, Bumjun Kil, who is a PhD candidate in the Department of Marine Science at the University of Southern Mississippi. Bumjun?
Thank you, Jennifer. Okay, I'm still seeing my presentation. Just one moment. Okay, thank you, Jennifer. Hello, my name is Bumjun Kil from University of Southern Mississippi, and thank you for joining Giovanni Workshop today. Now, I'm going to talk about advection of fluvial source into the center of Gulf of Mexico after tropical cyclone Isaac. This topic is dealing with the elevated optical signature in the open Gulf of Mexico, seen in this image after tropical cyclone Isaac. As you can see this image, it seems like this significant optical string seems like driven by tropical cyclone Isaac, but in this presentation I will show you and the origination of this optical tail is from the coastal advection. It is well known that upwelling due to tropical cyclone can lead an elevated optical signature in the open Gulf of Mexico. Chlorophyll A enhancement can result from vertical mixing and upward entrainment of phytoplankton from the deep cold water to the surface due to strong wind by tropical cyclone. Tropical cyclone Ivan shows a good example for triggering such a phytoplankton bloom driven by upwelling. Offshore advection of the shelf water to the open Gulf of Mexico was also studied as a probable origination because of high optical feature found on the eddies. James Ecker found that the elongated high optical signature in the open Gulf of Mexico around 2 weeks after the tropical cyclone Isaac in 2012 and described it as an optical tail. With regard to this optical tail, he also suggested the probability of its relating to advection of outflowing Mississippi River. Then why is this optical tail significant? If the river discharge with high concentrated dissolved nutrients increases due to heavy precipitation, specifically after landfall of the tropical cyclone, it can optically appear like a phytoplankton bloom during the river plumes away off the shelf. So that was Ecker's hypothesis. And try to answer that hypothesis, we utilized the remotely sensed salinity because of its ability to distinguish between a bloom fed by fluvial input and one fed by upwelling. Thus, the purpose of this research is to answer the Ecker's hypothesis, chlorophyll A, sea surface salinity, and CDAM absorption should be examined in order to demonstrate the advection of coastal water in the optical tail and Gulf of Mexico. In this research, we used in situ and the remote sensing measurement. As shown in the table as in situ measurement, we used trajectories of the drifting buoys that were deployed closely before the storm arrival. We also used the stationary measurements of in situ current and the river discharge. Because it is challenging to clarify the origination of the optical tail using a single remote sensing measurement, we employed multiple satellite measured variables As shown in the table, we employed chlorophyll A and CDAM absorption from the aqua models, and rain rate from TRIM, and sea surface salinity from the SMOS, and blended wind from NOAA sea winds, and surface geostrophic velocity from VISO. We specifically use the Giovanni system for time series analysis for chlorophyll A. To estimate the CDAM, which means as an absorption due to yellow substance at the 412 nanometers, we used Moran and Gently's case 1 water algorithm, which requires a CDAM index and the chlorophyll A. Because the drifting buoy were deployed before the tropical cyclone arriving, we simulated the presumable trajectory following the passage of Isaac. We used Euler and the longitudinal methods to estimate the trajectory based on surface geostrophic current derived from the satellite archimetry. We compared the SMOS and the MODIS product by time series and spatial collocation for optical tail issue region. Now, this is the result from the in situ measurement. The drifting buoy and river discharge and the current data to show the Mississippi River's plumes outflowing condition to the open Gulf for Mexico. The actual drifting buoy A, drifting buoy trajectory A and B took around 11 to 18 days for arriving the center of Gulf of Mexico. But despite the different date of deployment, the trajectories are very similar and showed advection from the shelf out to the offshore region. If the river plume expanded toward the starting point, A or B, it should follow the similar trajectory driven by surface currents. In terms of stationary measurements, the Mississippi River discharge reached its highest value on the August 30th. And this happened right after the tropical cyclone passing. And the subsurface current of the Mississippi River Delta, right here at this point, presented southwest and the southward flow after the peak of the Mississippi River discharge. Although it's subsurface, this is depth subsurface, these currents indicate appropriate condition for the advection of river plume toward the offshore. This picture are from the NOAA blended ocean winds. As you can see this picture, the picture is from the after tropical cyclone. The strong southerly wind over 20 meters per second were observed during the date of the rapidly increased the river discharge and 29 to 30. This strong wind must have driven the Ekman flow to the east. Thus, we can presume that the river water was extended eastward directing to the starting points A or B. Now, let's talk more about the Ekman flow. What is Ekman flow? At the surface, the ocean is acted upon by the wind stress. So Coriolis force and the frictional drag affect the water beneath the surface. In the steady state, the northern hemisphere, the ocean surface current flows to 45 degrees to the right direction from the wind direction, from the surface down to the depths until the currents go to the zero. We call it Ekman depth. The fluid moves more to the right as the depth gets deeper and the current becomes weaker. So we call it Ekman spiral. So this surface wind frictionally affect the seawater reaching around 100-meter depth. So ocean wind is very important and major forcing for shelf water by causing the Ekman flow. As shown in the superimposed chlorophyll A over the surface geostrophic currents, the highly concentrated chlorophyll A in the southern area of the Mississippi River Delta appears to be rapidly extended the south and the southeastward with offshore jet between two counter-rotating eddies. Over time, the offshore jet moves to west, and elevated chlorophyll A feature becomes less prominent. So we cannot see this kind of very highly concentrated chlorophyll A as time goes right here. And this picture is a 9-day composite sea surface salinity. The sea surface salinity shows a low salinity feature, which is similar with elevated chlorophyll A, especially from the August 30th to the September 13th. So as you can see this picture, when chlorophyll A extended offshore, the low salinity water also shows the same pattern as offshore moving. So the low salinity plotted over the surface geostrophic current shows the plume of fresh water of the Mississippi River Delta extending rapidly to the southeastward to maintaining the salinity less than the 34 PSU. In addition, the extending of this low salinity feature with elevated chlorophyll A shows a similar pattern with a trajectory in the actual drifting buoy in this way here and here, and also like a chlorophyll A in the similar pattern in the direction. So the coastal sources in the low salinity with enriched chlorophyll A might have been advected southeastward driven by a surface geostrophic current. Then why is the salinity less than 34 PSU significant? Because they indicate coastal sources, the extending fresh water as an impact of the peak of the Mississippi River discharge was discussed from the airborne measurements. And the low salinity water, which is less than the 34 PSU, was reported as extending offshore into the center of Gulf of Mexico after the peak of the Mississippi River discharge. That feature was observed by both SMOS and a Cryos satellite. Thus, the low salinity less than 34 PSU is presumable indicator as a fluvial source. And remember, the sea surface salinity can be used as an indicator as dissolved nutrient from the river. So, which means salinity value less than 34 PSU is more presumable indicator as indicating the nutrient, dissolved nutrient from the river water. Now let's go back to the result and talk more about the trajectory. The trajectory for the September 1st to September 22nd was simulated from the beginning location of actual buoy trajectories. As a result, the trajectory T1 and the T3 by Euler method and T3 by longitudinal method showed less than 20 days toward the center of Gulf of Mexico. As potential path of the offshore advection, we selected T1 in the Euler method, and we selected T3 in the longitudinal method, and then we superimposed to the chlorophyll A with a surface geostrophic current during optical tail events from the August 28th and the September 12th. And as shown in the figures, the both selected two trajectories simulated similar offshore extending with chlorophyll A. Consequently, the low salinity water with enriched chlorophyll A might have been advected from the Mississippi River Delta along the nearest eddies. For the period of the September 5th and September 13th, the water with elevated chlorophyll A and the low salinity water was also apparently away from the tropical Isaac's path. So this means, right here is the low salinity water and high chlorophyll A. This means low salinity water is the condition represent free from the tropical cyclone, the forcing, which induced the vertical mixing and upwelling. So that means it water condition right here is a strong stratification. So in the meantime, this low salinity, we also can think this low salinity can be resulted by heavy rainfall. So we need to check how does the low salinity water was affected by the heavy rainfall. But as you can see this picture right here, the low salinity was indicated by the low salinity anomaly, negative anomaly, was showing off from the heavy precipitation. So consequently, this low salinity water and the chlorophyll A have coastal relationship with each other in the optical tail region. The low salinity indicated by negative anomaly. As you can see, this black contoured line is corresponded to the positive chlorophyll A anomaly, and it's colored the picture as the yellow to the red colored picture, and appearing like a string. So we experimentally established the red colored box as indicated box C and the journal section A and B for time series comparison. So the journal for this time series comparison A and B, we will use the Hofmöller diagram. So I'd like to show you at first. I'd like to show you the Hofmöller diagram at first. It is challenging to find the significant features using a Hofmöller diagram because it takes a long time analyzing the numerous amount of digitized products. But thanks to NASA Giovanni visualizing system here, we can quickly look at synoptic description for a journal section A and B. So as you can see this slide, Giovanni presented elevated chlorophyll A anomaly right here, and it's elevated chlorophyll A. So the same picture, the journal section. So we can find this the elevated chlorophyll A feature, but also in showing a high anomaly in the 87 to 87.5 degree west, right after tropical cyclone Isaac. So in the meantime, the lowest peak of the salinity after tropical cyclone Isaac, which was showing less than 34 PSU. Remember that I said less than 34 PSU is a very important indicator for the coastal sources. This appeared simultaneously with highest peak of the CDAM absorption. Here this high CDAM absorption in the optical tail might indicate the heterogeneous source which was originated from the coastal advection. So it is significant to detect the coastal source in the open Gulf by comparing with a different satellite-borne the sea surface salinity from the SMOS and the CDAM from the aquamodis. The average chlorophyll A and the sea surface salinity and the CDAM absorption during the event of the optical tail is showing a box C, the red box. The high amount of the chlorophyll A right here and the CDAM in the optical tail was observed in the September 8th to 10th. And this time shows a similar more likely due to coastal sources because of the constant presence of the low salinity water, which was measured by small satellite, which is different satellite measurements. So in the scattered stem plot, we separated two groups as presence of the optical tail, which is August 8 to 10th, and the after optical tail event for the same box area collocated the sample. So as shown in the 3D stem plot, the chlorophyll A in the optical tail group tends to increase as sea surface salinity decreasing with the peak of the CDAM absorption. In contrast, this feature presented less prominence after the optical tail event. Accordingly, optical tail suggests its origination from the coastal water. In summary, the clear evidence of the coastal sources in the Gulf of Mexico after tropical cyclone Isaac was presented by the multiple satellites and in situ measurement. We found that the coastal sources in the center of Gulf of Mexico was originated from the consort of the peak of the Mississippi River discharge and the strong southerly wind and offshore jets between counter-rotating offshore eddies in the coast of Louisiana. The pattern of actual buoy trajectory consistently maintained offshore advection by simulating the trajectories based on the geostrophic, the surface flow. And the sea surface salinity and the CDAM absorption in the Gulf of Mexico were negatively corresponded with each other during the optical tail event. And as acknowledgement, I'm greatly thank the Republic of Korea Navy for as a good sponsor, and also greatly thank the NASA for providing optical satellite measurements and also inviting me as the Giovanni workshop, and also greatly thank European Space Agency and the SmallSpec and the NOAA for providing me providing the winds and the drifting data set, and USGS for providing a river discharge and also satellite measurements as the providing a geostrophic current measurement. And also you can find my topic in the MTS journal in this volume 48. Yep, that's it. Thank you very much for my presentation. Thank you.
Okay. Thank you very much, Bumjun. So now what we will do, we are a couple minutes early. I don't know, Jim Acker, if you're on the line, we could go ahead and move to the question and answer period now. Would you like to go ahead and do that?
Yes.
Okay. Okay, so let's go ahead and move to our question and answer period for our current speaker, Bo. If you have any questions, please go ahead and enter those into the Q&A pod on the right-hand side of your screen. And you will notice that I do have his presentation uploaded below in the file sharing pod. If you were to highlight that presentation, you would then have the opportunity to download that file. So we will now take any questions. Any questions for our speaker? Okay. Hold on a second. Okay, so one comment that you have here, Bumjun, is we have seen the offshore movement of the Mississippi River plume without a hurricane.
Yes.
Yes, that was one comment that you had, meaning southward motion to Key West.
Could you explain that again, please?
So it's more of a comment by one of the participants, not a question. And what he says is, He says that we have seen the offshore movement of the
Hmm?
Mississippi River plume
Hmm?
without a hurricane.
Yeah, that was introduced by the Girak, and can I show the picture in my presentation file?
Sure. Let me get back to that. No problem.
Yep.
Hold on momentarily. There you are.
Yeah. Yeah, that's a good question. I'll show you the picture. Actually, the offshore movement of the river water out to the center of Gulf of Mexico was it's common, like a common event because it was already introduced by the Iraq by using same small and Aquarius the satellite measurements. Uh, it was also commented that just one moment. Yeah, uh, this low salinity feature was occurred by the peak of the Mississippi River discharge. This was described as 1 and 2 months after the Mississippi River peak of the discharge. But the thing is, the Mississippi River discharge at that moment is like an annual climatological signal, like a climatological signal is annual the increase of the Mississippi River discharge. But the research, in my presentation, I'll show you just one moment.
Yes,
Yeah,
that's okay.
yeah. In my presentation, we can see this peak of the Mississippi River discharge is very short moment. Uh, This peak of the Mississippi River discharge is the Mississippi River discharge can be seen as annual signal, annual like during in the summer season. We can see this kind of the peak of the Mississippi River discharge, but this discharge can occur very long time. But in this presentation, I'm showing you the peak of the Mississippi River discharge driven by the hurricane induced rain rate. So
Okay.
uh,
So then just to add,
hmm?
there was an addition to the comment by Mitchell Roffer, and he said that
Hmm?
this occurs when there is a relatively large loop current eddy that
Hmm?
pulls the water southward to the loop current and then to Key West. So it's
Yes.
more so just a comment.
Go to the Key West, right here, right? Yeah. Are you hearing me?
Yes, I hear you.
Yeah. So yeah, I'm understanding. The loop current eddy also can be occurred by it's like the seasonal movement, seasonal the issue. The loop current eddy right here is that can be occurred uh, a little more to the coast of the south of Louisiana, uh, but that can be occurred in the summer season. So in the such as the fall and winter season, that eddy gyre system is much away from the coast, but during a summer season, we can easily see the loop current eddy system more close to the Mississippi River Delta. So we can find the offshore advection of this kind of the nutrients, optical enriched water advection to the offshore. We can see it, but uh, but it is very difficult to identify if it is really coastal sources or not because in the previous measurement, what you can see is using the aquamodis satellite, and we can just identify by using the visible band satellite. But now we can see this kind of advection of coastal sources by using the small satellite, and also Aquarius satellite also available. Uh, but the in the Girac research right here, okay, I'll show you again. Yeah, this measurement is captured by the monthly measurement, and also in this research, they cannot find the perfect match between the CDAM and the C-surface salinity. So actually, we can find chlorophyll A expanded after after Mississippi River peak of the Mississippi River discharge, but that high elevated amount of chlorophyll A can be increased, can be occurred not only for the offshore advection, but also from the upwelling or the vertical mixing events. So it cannot clearly identify that chlorophyll, the increased amount of chlorophyll A is originate from the river water or the open source, we don't know. So in that case, we have to compare it with sea surface salinity and the sea down absorption.
Okay, wonderful. Thank you, Bumjun. So the next question is from Dr. James Acker. He's asking you whether or not your final image in your presentation is of Tropical Storm Isaac.
Yes.
So the question is, so I guess it is.
Mm-hmm.
And Jim was saying that, he takes a fatherly attitude toward this presentation. Mitchell Roffer pointed out the counter-rotating eddies were present because of the unusual configuration of the loop current. I was hoping that you could point that out. Yeah. And then, let's see, this paper. Yes, so Mitchell further added that you provided an excellent diagnostic explanation. Mm-hmm. Okay, so let's move to our next question. Mm-hmm. Can we use, okay, ready?
Yes.
Okay, can we use any other marker to measure the surface currents except chlorophyll A?
Surface current, just one moment. Let's see.
So the question is whether or not you can use any other marker to measure the surface currents except chlorophyll A.
Well, I'm understanding the surface current, right? Without, mentioning about the current without chlorophyll A, or could you say that again, please? I'm sorry.
That's okay. Let's see. Normally the best product. Okay, so Jim Acker said normally the best product is sea surface temperature. Yes. I think what the participant was asking, are there any other markers that you can measure apart from chlorophyll A? Is that what you meant, Kate? And so Jim has said, has added to that by saying, normally the best product is sea surface temperature. So Kate, have we answered your question? If not, could you please further clarify within the Q&A pod? Okay. I don't see any additional commentary. Okay, thank you, she said. Okay, great. Are there any additional questions? Okay, let's see, another comment. Jim is noting that this was an unusual condition where the chlorophyll A product followed the current, excuse me.
Yes. Can I a little bit be specific about that comment?
Sure.
Yes. We can. The chlorophyll A also can be superimposed with model and also the satellite altimetry born the geostrophic currents, and it is right. It's very difficult to compare the chlorophyll A over the geostrophic current like this kind of offshore advection, because there are when a hurricane the passing through that region, and there are still amount of the cloud over there, so it's very difficult to compare the chlorophyll A over the surface current movements, because if heavier amount of cloud keeping it stationary moving, for that case it is difficult to identify. So even if we can find in this, like shown in this presentation, even if we can find this result, advection pattern, curve A, following the geostrophic current, as you can see, this we can still have the data missing right here. So in order to more clarify this event is not from the hurricane-induced forcing and for certain regions from certain origination from the coastal region, we can support that idea by comparing with another satellite. It's showing the picture in this kind of the small satellite. The good point of the small satellite is it is L-band radiometer. Which means it's measure the sea surface salinity in the microwave. Microwave can penetrate the cloud. So that is a good point because even if we cannot find the clear feature due to cloud, when we see the curve A or see them, we make it more clarify by comparing with the low salinity. So it is very significant because we can not only compare the curve A with the geostrophic current, but also we can match comparing with the sea surface salinity from this L-band radiometer. It's very useful measurement.
Okay, thank you, Bumjun.
Yes.
Any additional, let's see. Oops, excuse me, let me go down some more. Let's see. Okay, Jim Acker's comment is that they should be getting Aquarius salinity data into Giovanni through the Federated Giovanni project.
Yes, that is a good idea, use the Giovanni product right here because it also was already been introduced this kind of low salinity water by coastally induced low salinity water can be also detected by not only from the small satellite that I mentioned, but also can be can be measured by the Aquarius satellite. Yes, Aquarius satellite there's still kind of the difficulties because of its coarse resolution and also time is very, so around 1 week needed to measure the whole region. But we can measure this kind of low salinity events because it has the same sensor, same measurement pattern with the SMOS. I mean, the small satellite and Aquarius satellite has different measurement, but the retrieving methodology is the same pattern. So it also can measure the low salinity, less than 34 PSU, even if it has coarse resolution. So it is a very good idea use Aquarius, the salinity data to equip in the Giovanni. It is a very good idea.
Okay, wonderful. Thank you for your response.
Okay.
Are there additional questions for our speaker? I did jot down a quick note here, and that is that currently the Aquarius salinity data is being distributed through our NASA Physical Oceanography Distributed Active Archive Center, which is another one of the 12 EOS-DIS data centers.
Yes, I have comment about that. It is a very good idea. You can get the Aquarius data. The sources of Aquarius data is we can easily get that in the NASA PODAC. We can get the data by Google it as NASA PODAC, and we can the Aquarius, and we can get the FTP. And yes, Aquarius data is already it's been ready to use on the NASA PODAC web page, but that web page is just providing the digitized products. That means it does not give us like a visualizing product. Like I'm showing in here, and I showed you the Hoffman diagram right here. This diagram is not easy to plot by ourselves because we have to use MATLAB and we have to download lots of data product. But the good point of the Giovanni is showing that we don't need that long process. So by using also Aquarius data set, we can see the salinity feature by using a Giovanni system. So it is a good attempt to see see the sea surface salinity changes by using Giovanni, and then we can find more significant feature as progress. So it is good to reduce the time-consuming working. So it is a good system.
Okay, wonderful. So a couple more comments is that
Yep.
Dr. Acker said that he was wondering whether or not you referenced the 1993 river flood plume paper by Mueller-Karger. I'm not sure if I've pronounced that correctly. He's saying that that would be useful for your dissertation.
Oh.
You're quite welcome.
Yes.
Are there additional questions for our speaker? There are about 5 minutes remaining to this question and answer period, at which point we will then transition to a 15-minute break, and we will finish up with our last speaker for this afternoon. Any further questions? And Jim Acker said, thanks again, Bumjun.
Okay, thank you very much, Acker. We keep in touch then. Bye-bye.
Okay, if there are no further questions, then we'll go ahead and move to the, should move back to the, since we had jumped back to the slides, I will leave it on the file sharing pod for a moment for those of you interested in downloading the file. Again, you simply need to highlight the file, at which point the download option will appear. I'll leave it here for the next 3 or 4 minutes or so, and then we will be on 15-minute break. Okay, so be sure to stick around for our last speaker of day 2, Joanna Voinova, and I will introduce her after our break. Thank you so much, everybody.
Thank you. Bye-bye.
Thank you, Bumjun.
Bye-bye.